Right, and looks like everything is working the way it's supposed to be. All right, so today we are going to start on section 10.1, which covers power series and functions and how you can turn one into the other. Okay, so if you have a power series, it is just a series that has a certain form. So it's just a series. Let me kind of separate that a little bit. In the form, you have the sum from n equals 0 to infinity of some coefficient we'll call c sub n times x to the power of n. When x is equal to, well, not x, when n is equal to 0, you have your initial constant, or your constant term, plus c sub 1 times x to the first power, plus coefficient number 2 times x squared, plus coefficient number 3 times x to the third power, and it keeps on going. Okay. Where we know that your x is your variable and your c sub n is your coefficient. The thing about a power series is that for a power series, you may have some values of x where it's convergent and some values of x where it's not. Okay, so a power series may converge for some values of x and diverge for other values of x. Okay. Now another form of a power series is a power series that is centered at some value a. And sometimes it's also known as a power series centered about a. A power series about a. Just two ways of saying the exact same thing. Okay, and that has a similar form with one little change. So it has the form as the sum from n equals 0 to infinity of your coefficient times x minus a to the power of n. Okay, so that's the only difference between the two. This is a power series centered at 0, and this is a power series centered at some value a. So if a is equal to 0, then it's going to look like this one. And that's n is equal to 0. You just have your initial coefficient term, I mean, coefficient constant term, plus n is equal to 1. You have your first constant coefficient, well, coefficient term or constant. Nope, coefficient for your second term. That wouldn't be your constant coefficient since that one is. So x minus a to the first power plus your c sub 2 times x minus a squared plus, then you have c sub 3, x minus a to the third power, and it keeps on going. All right. So let's say, for example, if we want to find out for what values of x does the series, the sum from n equals 1 to infinity, x minus 3 to the nth power divided by n converge. Okay. So let's say if we decide to use the ratio test. So we're going to let our a sub n equal x minus 3 to the power of n divided by n. And we know that a sub n plus 1, that's just x minus 3 to the power of n plus 1 divided by n plus 1. Okay, so we know for the ratio test, we have the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n. Okay, well, that's just the limit as n approaches infinity of your a sub n plus 1, which is x minus 3 to the power of n plus 1 divided by n plus 1. Okay. So it's divided by a sub n, but we can take that division, change it to multiplication, and then we just flip the second fraction. Okay, so instead of a sub n divided by, well, a sub n plus 1 divided by a sub n, we get a sub n plus 1 times, and then we take the reciprocal of our a sub n. So that gives us n divided by x minus 3 to the power of n. So that x minus 3 to the power of n plus 1, we can rewrite that one. So we have the limit as n approaches infinity of the absolute value of x minus 3 to the power of n times x minus 3 to the first power, or just leave it as x minus 3, divided by n plus 1 times n divided by x minus 3 to the power of n. So this x minus 3 to the power of n cancels out with this one. So that gives us the limit as n approaches infinity of n times x minus 3 over n plus 1. And I'll just write it as n divided by n plus 1 times x minus 3. Okay. So since n is the only variable actually changing, we can factor this x minus 3, or the absolute value of x minus 3, just factor that out of the way and put it up front. So we have the limit as n approaches infinity. Oh, forgot to put my absolute value. I'll just put that there. The absolute value of x minus 3 times the limit of n divided by n plus 1. Okay. So if we divide each term by n, we'll find out that we'll have the limit of 1, which is just 1. So this limit just equal to 1. So we know that this is equal to, and I'll just bring this right on down. So we know the limit of the absolute value of a sub n plus 1 divided by a sub n as n approaches infinity is just equal to the absolute value of x minus 3 times 1, or x minus 3. So we know that, it's a little note, by the ratio test, the limit would have to be less than 1 to be convergent. So that means the absolute value of x minus 3 would have to be less than 1 to be convergent. And the absolute value of x minus 3, if it's greater than or equal to 1, it's divergent. Okay, so we're looking for the values where it's convergent. So we're going to set that the absolute value of x minus 3 is less than 1. And we can write that as a compound inequality. So we could just write that as x minus 3 can be between -1 and 1. Oops, should be just equal, less than. There we go. So if we want to just isolate x, we just have to get rid of that -3. So we add 3. Oops, to each section. So -1 plus 3 is 2, is less than x, is less than 1 plus 3, which is 4. So we know these are the values where it converges. Which means that if x is less than 2, or if x is greater than 4, those are the values where it diverges. All right, any questions on that one? Okay, so that brings us to what is known as our radius of convergence and interval of convergence. Okay, so what's if we had some given power series? And it's in the form that we know of n equals 0 to infinity of c sub n times x minus a to the power of n. We know you have 3 options. There are 3 possibilities. So the first possibility is that the series converges when x is equal to a. The second possibility is that every value of x is convergent. The series converges for all values of x. I swear this is going to be a long chapter if my phone wakes up every time I say series. Right. And the third possibility is that there is a positive number that we will call R. Where the series will only converge if the absolute value of x minus some number a is less than R. And it's divergent if the absolute value of x minus a is greater than R. And we kind of saw that with the last example. It was convergent when the absolute value of x minus 3 was less than 1, and it was divergent if it was greater than 4 and less than 2. Now that value R, that's your radius of convergence. Okay. Now for possibility number 1, that was just when your radius of convergence was equal to 0. And for possibility number 2, that's what happens when your radius of convergence is infinity, every possible value. Now the interval of convergence, that's where we wrote that as the compound inequality. That shows your interval of convergence. So the interval of convergence, a lot of times you'll see that as IOC, and the radius of convergence, you'll see that as ROC. So if you happen to see that, that's all it means. Okay, and this just consists of all values of x that are convergent. So x where the series converges. And clean that E up a little bit. Okay, so there are 4 possibilities of your interval of convergence. So it could be, first possibility, is a minus your radius, or a to a plus your radius, but it doesn't include those actual values. So we leave it as an open interval. Or it could be a minus the radius, a plus the radius, where this endpoint is part of your convergence, but the right endpoint isn't. Or it could be the other way around. Oh, let me look there. A minus R to A plus R. Clean up that A a little. Where the left endpoint is not convergent and the right one is. Or it could be that interval where both endpoints are convergent. Okay. So for the previous example, there was a reason I didn't call this the interval of convergence, because I didn't test the endpoints. So first thing you do if you wanted to find out whether or not this was the interval of convergence is you would find this, and then you plug 2 into your original series and see if it converges. Then you plug in 4 into your original series, see if it converges. Sometimes one will, sometimes both will, sometimes neither one will. But we still have to check the endpoints. Let's see, did I move that already? Okay, so let's say, for example, if we wanted to find a power series to represent the function f of x is equal to 1 over x plus 2. So we know that we have f of x is equal to 1 over x plus 2. Okay. But if you remember, we have your geometric series, which is going to come in very, very handy. Remember, that says if you have the sum from n equals 1 to infinity, a times r to the power of n minus 1, or you could have it from n equals 0 to infinity and have that r to the power of just n. Both of those would be right. Remember, it converges if the absolute value of r is less than 1. And if it converges, we know that the sum is a divided by 1 minus r. Okay, So what we have to do is we have to get this function and put it in this form. Okay, so if we have 1 over x plus 2, we want to rewrite that as 1 over 2 plus x. Okay, so we want to get this first term is just 1, which means we're going to have to factor out a 2. So we're going to get that, and we're going to rewrite that again as 1 over 2 plus, and instead of x, we're going to make it 2x over 2. Just so we have something to factor out. Okay, so if we factor out that 2, I figure I'll go ahead and start writing downward here, since we're going to eventually run out of space there. We have 1 over 2 times 1 plus x divided by 2. But remember, a lot of these formulas, you have to be precise down to the very last detail. So remember, this is 1 minus r. So we have to have that as 1 minus something. So that 1/2, we can just factor that out if you wanted to. So we have 1/2 times, and instead of 1 over 1 plus x over 2, we rewrite that again and make it 1 minus negative x over 2. Okay, so if you look at this, it's in the right form. It's in the form, but you can even get that 1/2 and bring it up top if you want to. A over 1 minus r. So we can see here, a is equal to 1/2 if we bring it up top. And the absolute value of r is equal to the absolute value of negative x over 2. Remember, the condition was that the absolute value of r had to be less than 1. So that means this absolute value of r has to be less than 1. Okay. So we know that when this is true, you know, the absolute value of negative x over 2 is less than 1, that's where it converges. Okay. So if we take our absolute value of negative x over 2 is less than 1, and you can get that negative 1/2 and factor it out. So you have the absolute value of negative 1/2 is just 1/2. So if we get our inequality and multiply both sides by 2, then we get the absolute value of x is less than 2. So if we rewrite that, we can rewrite that as a compound inequality of negative 2 is less than x is less than 2. So if we plug in our endpoints, because we know this is convergent for every value between there, but we don't know about the endpoints yet. Okay. So when x is equal to -2, well, we end up with, oh, actually, we have to convert that. Plug that into our -2. So if we plug it into our geometric series, we could actually see where you have -2/2. That absolute value is equal to 1. So remember, when that is equal to 1, it's inconclusive, and you have to use another test. Uh-oh. When we plug in +2, again, you'll end up getting the absolute value, which is just 1. So when x is equal to 2, it's also inconclusive. Remember, both of those give the absolute value of r is equal to 1. So since it's inconclusive for both of those, we can't include either one of those. So we know that our interval of convergence is just from -2 to 2. Let's see, I think I'm missing a page. Okay, I got it. All right, any questions on that one? Excuse me. All right. Okay. So let's say if we, for example, wanted to find a power series representation for f of x is equal to x to the third power divided by x plus 2. Okay, so we have f of x is equal to x to the third power over x plus 2. Let's rewrite that as x to the third power times 1 over x plus 2. Okay. The reason why is because we want to put this into geometric form. Which is 1 over a over 1 minus r. Okay. Well, luckily for us, we did that on the previous example. we know that this is equal to, draw a little arrow there, x to the third power times 1/2 times 1 over 1 minus negative x over 2. Move that little mark out the way. Now, once you have it in that form, just remember that the sum a divided by 1 minus r, that's just our geometric series a times r to the power of n. Okay. And remember, you can also put it in the form the sum from n equals 1 to infinity of a times r to the power of n minus 1. So both of those are true. Okay, so we know that our f of x is equal to x to the third power. And we know that our a is equal to 1/2. And let me make that over here. A is equal to 1/2. And r is equal to, well, the absolute value of r is equal to x over 2. Or in this case, negative x over 2. Because the absolute value is equal to x over 2. But we're just looking for r. Okay, so that's x to the third power times 1/2. And we're going to get our a and our r. Again, that a, we just go ahead and bring that out to the front. But the r, we know that is just going to be the sum, and we'll use from n equals 1 to infinity. It doesn't matter which one you use, but we'll use from n equals 1 to infinity. Of your a, which is your 1/2, that's why we just factored it out to the front, times your r, which is negative x divided by 2 to the power of n minus 1. I wonder if the fan is kicking on because it's, let me see what the temperature is. It might be just hot. I don't think I remember it cutting on this much before. Like I said, unless I zoned it out before, but it seemed like it's a. Oh, okay. I thought maybe it was just me, but yeah, it's making a lot more noise than usual. Okay. So now we get our function f of x is equal to x to the third power. And really, if you look at it, again, that 1/2, we can get that 1/2 and leave it factored out for now. The sum from n equals 1 to infinity. We could rewrite this as negative 1 times x divided by 2 to the power of n minus 1. Okay, so negative 1 times x divided by 2 to the power of n minus 1. Okay, so if we apply this exponent to both of the factors, that'll be -1 to the power of n minus 1. We have 1/2 times the sum from n equals 1 to infinity of -1 to the power of n minus 1. Times x divided by 2 to the power of n minus 1. Okay, so if we want, we'll distribute that first and then I'll write it just to avoid confusion. So we can distribute that. We can have f of x is equal to x to the third power times 1/2 times the sum from n equals 1 to infinity of -1 to the power of n minus 1 times x to the power of n minus 1 divided by 2 to the power of n minus 1. Okay, so now if we get these 2's and we multiply them together, and we get x to the third power and multiply with that x to the power of n minus 1, then we can rewrite that function as f of x is equal to, I'll just leave that 1/2. Well, actually, if we combine it, we can get rid of that, which makes it a lot easier. So we have the sum from n equals 1 to infinity of -1 to the power of n minus 1. And we have x to the third power times x to the power of n minus 1. We have x to the power of n minus 1 plus 3. So we have x squared. Divided by 2 to the power of n minus 1 times 2 to the first power. That's 2 to the power of n minus 1 plus 1. So it's 2 to the power of n. Oh, not x squared. I mean n plus 2. So it's n plus 2. Because it's n minus 1 plus 3, not x squared. Duh. Okay, so we can leave, let me clean that up a little bit. And plus 2. There we go. Okay. So if you want it, you could leave it like that, or you can make it f of x is equal to the sum from n equals 0 to infinity of -1 to the power of n. Times x to the power of n plus 3. And the best way to look at it is plug in your 1, you get x to the third power. If you plug in 0, you still get x to the third power. Okay, so here if you plug in 1, you get 2 to the first power. Here if you plug in 0, you'd have to have 2 to the power of n plus 1. Plug in 0, you'd still get 2 to the first power. So both of those are true. Let me move that or out of the way a little bit. Make it a little bit higher. There we go. Same thing with the -1. If you plug in 1, you get -1 to the power of 0. If you plug in 0, you get -1 to the power of 0. So you get the exact same terms. All right, any questions on that one? All right. Anyone still writing? All right, let's finish up. All set. Okay, you're welcome. Okay, so that brings us to section 10.2, which covers the properties of power series. Properties of power series. And really, a lot of the properties are similar to those of derivatives and antiderivatives, so they should look somewhat familiar. And the first is the sum or difference property. And this is just of two series, or two power series. Make sure I identify that two power series. Okay. So if we have a power series, we have the sum from n equals 0 to infinity of your coefficient times x to the power of n. And if that equals some function f of x, kind of like we did before. And what if we have another power series, but we'll call the coefficient d sub n times x to the power of n. Let's say that equals some function g of x. Okay, then we know that if we add those two together, so if we take the sum from n equals 0 to infinity of c sub n times x to the power of n, and either plus or minus your coefficient d sub n times x to the power of n, then that's just going to equal your f of x plus or minus your g of x. If you just distribute that summation. So let's say if you did add those two series and you wanted to find the interval of convergence for their sum or difference. Okay. Well, the interval of convergence will just be the intervals that intersect of your f of x and your g of x. So if f of x is convergent from 3 to 4, so let's say 3 to 5, and g of x is convergent from 4 to 6, then the intersection that would be true for both would be the intersection of convergence for the sum. So it would be 4 to 5. Okay, so you take this intersection and this intersection, see where they're the same, and that's your interval of convergence. Interval of convergence of any two series or any two power series is the intersection, move that up a little bit, of their individual intervals of convergence. And again, just a little side note that may come in handy later. All right, anyone else still writing? All right. Okay, so let's say, for example, what if we let the power series, the sum from n equals 0 to infinity, of a sub n times x to the power of n, converge on the interval from negative 1 over 4 to 1 over 4. And we know the power series, the sum from n equals 0 to infinity. Uh-oh, kind of a messy looking infinity. Here we go. Of b sub n times x to the power of n. We know that this converge on the interval from negative 1 over pi to 1 over pi. So we want to find the interval of convergence for the sum from n equals 0 to infinity, a sub n times x to the power of n, plus b sub n times x to the power of n. Okay, so we know that the intersection, I might as well just say interval of convergence. No point in saying the intersection. So the interval of convergence for the sum from n equals 0 to infinity, a sub n times x to the power of n plus b sub n times x to the power of n is just the intersection of their individual convergence or intervals of convergence. So that means if you get negative 1/4 to 1/4, you want to find their intersection with negative 1 over pi times 1 over pi. And just a little note on the side here. So make that a little neater. It's kind of like an upside down U. That's your intersection. And this is your union. Or you can think of this as your and this as your or. Okay. So for me, what I always do is I love number lines because they give you something to visualize. Okay. So let's look at, let's say this is our 0. Let's say this is negative 1/4 and positive 1/4. Okay. So because these both have parentheses, we know it doesn't include negative or positive 1/4. So we're going to draw parentheses there. Okay, so we know that that is the interval of convergence for the first power series. Okay. Now, if we take negative 1 over pi, well, we know that is, plug that into a calculator, you get negative 0.31831. Plug positive 1 over pi into your calculator, you get positive 0.31831. Plug negative 1/4, you get negative 0.25. And you get positive 0.25. So we know that for this interval, every value in between there belongs in their interval of convergence. Okay, so the only interval that would be true for both of these is the interval right here. This is the only interval that's true for both. And that's from negative 1 over 4 to positive 1 over 4. So they both have a common interval of convergence. And that's from negative 1 over 4 to positive 1 over 4. Excuse me. All right, any questions on that one? right, so this one was pretty straightforward. I don't think it was anything too tricky about this one. Okay, now with this example, let's say if we wanted to find a power series for f of x is equal to 14x plus 6 divided by x squared minus 1, centered at 0. And we want to do that by adding two power series. Okay. But we know that our f of x is equal to 14x plus 6 divided by x squared minus 1. Okay. But that denominator, we have a difference of squares. So we can actually rewrite it as 14x plus 6 divided by x minus 1 times x plus 1. Which is very helpful because we want to create a power series, but we need two of them. So that means we have to convert this to two separate functions so we can create two separate power series. So we want to convert f of x to the sum of two functions. Okay, so that should look familiar because what we're going to use are partial fractions. Okay, so we're going to use the partial fractions for the non-repeating linear denominator factors. So we can get our 14x plus 6 divided by x squared minus 1. And we can rewrite that. Actually, we can factor that, and this way it'll be a little more understandable. X minus 1, x plus 1. We're going to rewrite that as some value a divided by x minus 1 plus some value b divided by x plus 1. So the first step for our partial fractions is we have to get a common denominator. We have our 14x plus 6 divided by x minus 1 times x plus 1 is equal to a divided by x minus 1. We're going to multiply that by x plus 1 over x plus 1. plus b divided by x plus 1. We're going to multiply that by x minus 1 over x minus 1. So once we have our common denominator, we know that if we multiply each term by that common denominator, all of those denominators will cancel out and just equal 1. Excuse me. So that gives us 14x plus 6 is equal to a times x plus 1 plus b times x minus 1. So we're going to go ahead and use strategic substitution because it's a lot faster. You don't have to use it. You can use matching coefficients, but we're just going to be using strategic substitution. Okay, so we know x plus 1, we want to make that equal 0, and x minus 1, we want to make that equal 0. So what if we make x equal, I'll say let x equal negative 1. Because that would make this term equal 0. So that gives us 14, instead of 14x, 14 times negative 1 plus 6 is equal to a times negative 1 plus 1 plus b times negative 1 minus 1. Okay, so we have negative 14 plus 6, so that gives us negative 8, which is equal to negative 1 plus 1 is 0, so that disappears, plus negative 1 minus 1 is negative 2, so that's minus 2b. So if we divide both sides by negative 2, we end up with b is equal to 4. Okay, so now we do the same thing. We let we let x equal positive 1. And that gives us 14 times 1 plus 6 is equal to a times 1 plus 1 plus b times 1 minus 1. Oh, 1 minus 1 is 0, so we know that term just disappears. So 14 times 1 is 14. 14 plus 6 is 20. So we have 20 is equal to 1 plus 1 is 2, so that's 2a. So if we divide both sides by 2, we can see that a is equal to 10. So we know that our f of x, which is originally equal to 14x plus 6 divided by x minus 1 times x plus 1, we can rewrite that by replacing our a with 10. So that'll be 10 over x minus 1. And replacing our b with 4, so that'll be 4 over x plus 1. So plus 4 over x plus 1. Don't really need the parentheses there. Don't know why I put them. X plus 1. Okay, so we have that one function that we now split into two. So we have to convert both of those functions to their own personal power series. And we're going to go to Old Faithful, the geometric series for that one. So we know that the sum from n equals 0 to infinity, and make that a little neater, a times r to the power of n, we know when it converges that their sum is equal to a over 1 minus r. When it converges. Okay, so we have to put both of these into this form. Okay, we have 10 divided by, actually I'll put it on the next page. Just instead of trying to squeeze it all in that 1.5 inches of space. All right, I figure everyone should be done writing. So if we want to put it in our geometric series form, we have our 10 divided by x minus 1. Okay, so we can rewrite that as 10 divided by, if we switch those two up, -1 plus x. And remember, we want it in the form a divided by 1 minus r. So if we divide each one of those by -1, so 10 divided by -1, divided by -1, divided by -1, plus x divided by -1. Well, that gives us -10 divided by, negative divided by negative is positive, so 1 minus x, which is just the form we needed, a over 1 minus r. So for this one, we see that a is equal to -10, and r is equal to x. And because we're using two of them, I'll say a number 1 and r number 1 just to separate the two. So a number 1 and r number 1. Because we have two separate functions that we're converting to a power series. So just to avoid confusion. And our next one, we have 4 divided by x plus 1. Do the same thing. We want to put it in that form. So we're going to make that 4 over 1 plus x, which we can just rewrite it as 4 over 1 minus negative x. So we can see for this one, we'll call this a number 2. We know that's equal to 4 because that's in the same form. Our R number 2, we see that's just equal to negative x. So that means we can take our f of x that equals 10 divided by x minus 1 plus 4 divided by x plus 1, and we can rewrite it as f of x is equal to negative 10 divided by 1 minus x. Plus 4 divided by 1 minus negative x. Okay, so we can see for this one, a number 1 is equal to negative 10, and r number 1 is equal to x. And for this one, a number 1 is equal to 4, r number 1, a number 2. R number 2 is equal to negative x. So now we know that we could take our function f of x and convert that to a power series from n equals 0 to infinity of a number 1 times r number 1 to the power of n plus the sum from n equals 0 to infinity of a number 2 times r number 2 to the power of n. So we're going to take that function and rewrite it as the sum of two power series. So that means we can rewrite it as the sum from n equals 0 to infinity of our a number 1, which is negative 10, times r number 1 to the power of n. So that's just x to the power of n. And you didn't need the parentheses. I don't know why I did that, but it doesn't hurt. But don't need them. Plus, we have the sum from n equals 0 to infinity of a number 2, which is 4, times r number 2 to the power of n. So that's all. This one you do need the parentheses because you have negative x to the power of n. Okay, so this is our next version of f of x. Okay, so this negative 10, we can go ahead and factor that out to the front. So we have f of x is equal to negative 10 times the sum from n equals 0 to infinity of x to the power of n, plus Now this negative x to the power of n, remember, we can rewrite that. Because if you have negative x to the power of n, you can rewrite that as negative 1 times x to the power of n. And you can distribute that exponent to both factors. So that becomes negative 1 to the power of n times x to the power of n. So this just becomes 4. We just factor that 4 out to the front, times the sum from n equals 0 to infinity. And that negative x to the power of n, we just rewrite it as negative 1 to the power of n times x to the power of n. Okay, so we factor out the summations. We can have f of x equal the sum from n equals 0 to infinity of negative 10. And we can factor out the x to the power of n also, but we'll put that on the other side. Negative 10 plus 4 times negative 1 to the power of n times x to the power of n. Or if you want, you can distribute the x to the power of n to those two. It doesn't matter. So you can have it in this form or distribute that. So f of x is equal to the sum from n equals 0 to infinity of negative 10 times x to the power of n plus 4 times negative 1 to the power of n, x to the power of n. And again, like I said, either form will work. All right, any questions on that one? All right, anyone still writing? Looks like everyone's done. Okay, so let's say if we want to determine the interval of convergence for the power series, that can be represented, or that can be used to represent the function f of x is equal to 15x plus 11 divided by x squared minus 1 centered at 0. Okay, so to find the interval of convergence, we use the same process. we have to find out if you can separate that into two separate functions and if each one happens to have their own interval of convergence. Okay, so once again, we're going to do the same thing we did before, but we're going to take it a step further at the end. So that 15x plus 11 divided by x squared minus 1, remember that's just x minus 1 times x plus 1. We're going to rewrite that as some value a divided by x minus 1 plus some value b divided by x plus 1. So it starts off pretty much the same way, but then it kind of takes a different turn at the end. Okay, so we know that we can take our 15x plus 11 divided by x minus 1 times x plus 1. We can write that as a over x minus 1 times x plus 1 over x plus 1 plus b divided by x plus 1 times x minus 1 over x minus 1. And we know if we multiply them each by the greatest, well, the common denominator, not even the greatest, the common denominator, those will all cancel out. So we have 15x plus 1 is equal to a times x plus 1 plus b times x minus 1. So once again, we're going to use strategic substitution. So first, we're going to let x equal 1. And make that equal sign a little neater than that. So we have 15 times 1 plus 1 is equal to a times 1 plus 1 plus b times 1 minus 1, where that 1 minus 1 is 0. Oh, 11. That should be 15 plus 11, not 15 plus 1. I was thinking of that x equal 1 and wrote 15 plus 1. So make sure it's 15x plus 11. Okay. So 15 plus 11, that gives us 26. We have 26 is equal to 2 times a. Divide both sides by 2, we have a is equal to 13. So once again, if we let x equal negative 1, then that gives us 15 times negative 1 plus 11 is equal to a times negative 1 plus 1 plus b times negative 1 minus 1. So negative 15 plus 11 is negative 4. It's equal to negative 1 plus 1 is 0, so that disappears. Negative 1 minus 1 is negative 2, so negative 2b. Divide both sides by negative 2. We know that b is equal to 2. So once again, we know that our f of x, which is equal to 15x plus 11 over x minus 1 times x plus 1, we are able to rewrite that as a divided by x minus 1, or 13 divided by x minus 1, plus b divided by x plus 1, or plus 2 divided by x plus 1. But remember, we want to put it in geometric form. So we have a geometric series from n equals 0 to infinity. A times r to the power of n. When it's convergent, if a divided by 1 minus r, when the absolute value is less than negative 1, it converges. Okay. So we didn't need that absolute value of r on the last question. I mean, it was there, we just didn't use it. But on this one, because we're looking for the interval of convergence, we need that part. Okay, so if we take our 13 over x minus 1, we have to put it in that geometric sum form. Remember, we can just make that 13 over negative 1 plus x. So if we multiply or divide each term by negative 1, we get negative 13 divided by 1 minus x. Our a number 1 is equal to negative 13. Now r number 1 is equal to x. And we take our 2 divided by x plus 1, and we can rewrite that as 2 divided by 1 plus x. Well, we have to have it in geometric form, so we're going to rewrite that again as 2 divided by 1 minus negative x. So we can see here, we'll call this our a number 2 is equal to 2. Now our number 2 is equal to negative x. And finish it up on the next page. right. So we know that we can rewrite our f of x as the sum of those two functions. So we have our 13 over x minus 1 plus 2 over x plus 1 that we rewrote in geometric series form as negative 13 over 1 minus x plus 2 over 1 minus negative x. Where our a number 1 is equal to negative 13, and our r number 1 is equal to x. For this one, our a number 2 is equal to 2. Now our r number 2 is equal to negative x. So our f of x, we want to rewrite it as the sum from n equals 0 to infinity of a number 1 times r number 1 to the power of n. And make those ones a little clearer. Don't want them to look like commas. So a number 1 times r number 1 to the power of n plus the sum from n equals 0 to infinity of a number 2 times r number 2 to the power of n. Okay, so we can just make that the sum from n equals 0 to infinity. Our a number 1 is negative 13. So that's negative 13 times your r number 1 to the power of n. So that's x to the power of n. Plus the sum from n equals 0 to infinity of our a number 2, which is 2, times r number 2 to the power of n. So that's negative x to the power of n. Okay. So again, that negative 13, just going to go ahead and factor that out for no other reason than we want to. So negative 13 times the sum from n equals 0 to infinity of x to the power of n, plus, same thing with that 2, we're going to go ahead and factor that out to the front, times the sum from n equals 0 to infinity, and that negative x to the power of n, remember, you can make that negative 1 times x, and then just distribute that exponent. So it's negative 1 to the power of n times x to the power of n. I might send them an email to check that out. I don't want it to go out randomly.
Because it's hot today.
That's what I was wondering.
Usually it's cold in here.
Yeah, if it was just turned on because it's hot. But I've had one of those just conk out in the middle of class one time before. So
yeah.
that's why I just wanted to come by and check on it.
Yeah.
Just to make sure it's not going out. Okay, so just like we did before, we can rewrite our function f of x is equal to, factor out our summation. So we have negative 13 plus 2 times negative 1 to the power of n, and we'll factor out our x to the power of n. Okay. So really, this part was just kind of extra practice. To find the radius of convergence, we just need to have the absolute value of r be less than or equal to 1. I mean, less than 1. If it's equal to 1, it's inconclusive. Okay, so for a geometric series, we have the sum from n equals 0 to infinity. A times r to the power of n equals a divided by 1 minus r. We know it's convergent. The absolute value of r is just less than 1. Okay, so because I know they're going to throw more questions like this at you, that's why we went through those steps. But really, on this part, you could have solved this one because you have your R1 and your R2. Okay, so since the absolute value of R number 1 is equal to the absolute value of x, it has to be less than 1. You see that the interval of convergence would be, I don't even need the parentheses. I think I just put parentheses everywhere out of habit. Be from -1, less than x, less than 1. Okay, so again, if you plug in your endpoints, we could see that we would have, oh, where is it? Actually, it couldn't be -1 or 1 because they would both be divergent at those endpoints. Because if we made x equal 1, we can see that -1, it would just oscillate between positive and negative as n increases. So when n equals 1, it'll be positive, then it'll be negative, it'll just bounce around. So it really wouldn't converge to any particular point. Same with -1. You can see if we plugged it in, it would just kind of bounce around. It never would converge to any particular value. Okay, so we can see that our interval of convergence is from -1 to 1. And we know that since the absolute value of r number 2 is equal to the absolute value of -x, which is still x, is less than 1, we see that interval of convergence is still from -1 to 1. Because the absolute value of x and absolute value of -x, same thing. So we know that that interval of convergence is also from -1 to 1. And again, it wouldn't really involve keeping the endpoint, so you wouldn't have any brackets for the same reason as the first one. So because they're the same, we know the intersection is just the very same one. But just for the sake of showing the steps, you know, the interval of convergence for the sum is equal to the intersection of -1 to 1 and negative 1 to 1, which of course is negative 1 to 1. All right, any questions on that one? Excuse me. All right. So let's say, for example, if we wanted to find the first four, make that E a little bit neater. The first four terms, or let's say for our terms that are non-zero, of the product of the power series. Negative 2 divided by 1 minus x to the 7th power. And negative 3 divided by 1 minus x to the 6th power. To construct a power series for f of x is equal to 6 divided by 1 minus x to the 7th power times 1 minus x to the 6th power. On the interval from negative 1 to 1. Okay, so this one, of course, we're going to need the geometric series. Told you that one would hang around a lot. We have the sum from n equals 0 to infinity. A times r to the power of n, when convergent, is equal to a over 1 minus r, given that the absolute value of r is less than 1. So if you notice, I write it down each and every time, just habit from when I was a student. That's how I remembered it. I can't cram, so I have to put it into my short-term memory a little bit every day, and it just stuck. So you don't have to write it each and every time, but it does help. Take it from someone with a horrible memory. Okay, so now we get our negative 2 over 1 minus x to the 7th power. Well, that's already in our 1 minus r. We see that a number 1 is equal to negative 2, and r number 1 is equal to x to the 7th power. So we can just go ahead and plug that right on into our power series. So that's the sum from n equals 0 to infinity of a times r to the power of n. So that's negative 2 times x to the 7th power to the power of n. Okay, so we can get that negative 2, of course, just bounce that right to the outside, times the sum from n equals 0 to infinity. Yeah, that's an ugly infinity. Times x to the power of 7. And that to the power of n, that's just x to the power of 7n. Okay, and we do the exact same thing for negative 3 divided by 1 minus x to the 6th power. We see that our a number 2 is equal to negative 3. Our r number 2 is equal to x to the 6th power. So if we go ahead, we can just make that the sum from n equals 0 to infinity of a, which is negative 3, times r to the power of n, so that's times x to the 6th power raised to the nth power. Which is equal to negative 3 times the sum from n equals 0 to infinity of x to the power of 6n. So now we want to find the first four terms of each series. Okay, so if we look at our negative 2 times the sum from n equals 0 to infinity of x to the power of 7n, we plug in n is equal to 0, that's x to the power of 0 times negative 2, which is negative 2. We plug in n is equal to 1, that's x to the power of 7 times 1 times negative 2, so that's minus 2x to the 7th power. So this is n equals 0, n equals 1, and n equals 2. Plug in n equals 2, that's x to the power of 7 times 2, which is 14, times negative 2. This is negative 2x to the 14th power. We have n is equal to 3. When n is equal to 3, we have 7 times 3, which is 21, times negative 2, so that's minus 2x to the 21st power. And we only need the first 4, so we can leave it at that. I'm not too worried about the rest of them. And we do the same thing for this one. So we have negative 3 times the sum from n equals 0 to infinity of x to the power of 6 times n. Okay, well, when n is equal to 0, let me get rid of that parentheses there. That one looks a little bit. There we go, just to straighten that up a little bit. So when n is equal to 0, we have x to the power of 6 times 0. So x to the power of 0 is 1 times -3, which is just -3. When n is equal to 1, we have x to the 6th power times -3, so minus 3x to the 6th power. When n is equal to 2, we have minus 3x to the 6 times 2 power. Minus 3 when n is equal to 3. 6 times 3 is 18, so minus 3 times x to the 18th power. And it keeps on going. Okay, so the product of the series, or the product of the power series, well, that's just multiplying our -2 times the sum n equals 0 to infinity of x to the power of 7n. Ooh, I feel a sneeze coming on, trying to fight it off. Times the sum from n equals 0. I might put my -3 there first. -3 times the sum from n equals 0 to infinity of x to the power of 6n. Well, since we already have the first 4 terms of each, I'll just move the arrow down a little bit. Because no, that's just going to be -2 minus 2x to the 7th minus 2x to the 14th minus 2x to the 21st power, and it keeps on going, times those first 4 terms, -3 minus 3x to the 6th minus 3x to the 12th minus 3x to the 18th, and it keeps on going, but we are not concerned about those. So we're just multiplying the first 4 terms out of each series. And we'll continue that on the next page. All right. Okay, let's go ahead and finish this one up. And I'll just rewrite where we left off because we're going to need it. -2 minus 2x to the 7th minus 2x to the 14th minus 2x to the 21st times -3 minus 3x to the 6th minus 3x to the 12th minus 3x to the 18th, and it keeps on going. Okay, so we get this -2, and we multiply it to those four terms. Okay, so we have -2 times -3, which is +6. We have -2 times -3x to the 6th power, which is +6x to the 6th power. -2 times -3x to the 12th power, plus 6x to the 12th power. -2 times -3x to the 18th power is plus 6x to the 18th power. And it keeps on going, but we're not concerned with those. Okay, so we have those first four terms, plus, now we take this -2x to the 7th power, and we multiply that one by those four terms. So -2x to the 7th power times -3 is +6x to the 7th. -2x to the 7th times -3x to the 6th is +6x to the 13th. -2x to the 7th times -3x to the 12th is to the 19th power. Is +6x to the 19th power, plus -2x to the 7th times -3x to the 18th is 6x to the 25th power, and keeps on going, but we don't care about those. Okay, plus, we do the same thing with -2x to the 14th power. Just distribute it to each four of those. So we have -2x to the 14th times -3. So that's +6x to the 14th power. -2x to the 14th times -3x to the 6th. That's +6x to the 20th power. And -2x to the 14th times -3x to the 12th is +6x to the 26th power. Plus, since negative times negative is positive, we have +6 times x to the 24th power times x to the 18th power. Oh, 21st power, I said 24th. The 21st and the 18th, so that's the 25th, nope, the 18th, 39th power. Nope, I'm skipping one, I said 21st. That should have been, that's why I circled it. So that's the 32nd power. That's the exact reason I circled it, was just for an occasion like that one. And it keeps on going, but we don't care about those. Okay, plus, and we do the same thing for this very last one. We have -2x to the 21st power times -3, which is +6x to the 21st power, plus -2 and -3, well, -2x to the 21st and -3x to the 6th is 6x to the 27th power, plus -2x to the 21st times -3x to the 12th, that's 6x to the 33rd power. Make that 33 a little bit neater than that. Plus, we have -2x to the 21st times -3x to the 18th. That's the 6x to the 39th. And it keeps on going, but we do not care about that. So we're looking for the first four terms. Remember, they have to be in either ascending or descending order. So you can put them in either one. They'll usually tell you which order to put them in. So with this one, we'll put the first four terms in ascending order, which means our exponents will get bigger. Okay, so we're looking for the first four terms. Well, the first term would be 6. The next smallest exponent would be 6x to the 6th power. The next smallest exponent is 6x to the 7th power. So that one kind of moves you out of the idea of it going right across in that first row. And the fourth smallest exponent is our 6x to the 12th power. So those are the first four terms of the product. I dare you to tell me that wasn't fun. All right, any questions on that one? Oh, goodness sake, laugh. This class is stressful enough. I'm trying to take some of the pressure off a little bit. All right, no questions. All right, leave it up for a little bit. Let everybody finish writing. We put these up. All right. So we can probably won't finish 10.3, but we can at least start on it. So section 10.3, those are your Taylor and Maclaurin series. Check something real quick. 1 second, just want to double check something. Yep, we're good. Okay, so let's say if our function f has a power series representation at some value c. Before we used a, but we'll say it's c. So all that means is that it's in the form of f of x is equal to the sum from n equals 0 to infinity of our coefficient c sub n times x minus c to the power of n. Where we know that the absolute value of x minus c is less than r, where r is our radius of convergence. Okay. So if it meets these stipulations, then we know that the coefficient is given by the formula c sub n is equal to the nth derivative at c divided by n factorial. And make that n in parentheses. Okay, so that's just the formula for the coefficient. Okay, so every c sub n we can replace with this. So that just means that your f of x that is equal to the sum from n equals 0 to infinity of c sub n times x minus c to the power of n. We can rewrite that. We make n equals 0. So that's x minus c to the power of 0, which is just 1. Okay, so that's just your f of c. Or your f of x is just your coefficient. Plus, if you have your n is equal to 1, then that's your first derivative, f prime of c, divided by 1 factorial times x minus c to the first power. Plus, we have n is equal to 2. You have x minus c, I guess you can say the second derivative at c divided by 2 factorial for your c sub n times x minus c squared. Plus, when n is equal to 3, your third coefficient is the third derivative at c divided by 3 factorial times x minus c to the third power. And it keeps on going in that pattern. Now, this is called your Taylor series. The Taylor series of some function f at some value c. Or you can say the Taylor series centered at c. Again, just multiple ways of saying the same thing. Okay, so just a quick note. The Taylor series is also known as the Taylor polynomial. Let me clean that y up a little bit. So if you see Taylor series and you see Taylor polynomial, same thing. So what if we take that series and we just make c equals 0? Then we know that our f of x, which is equal the sum from n equals 0 to infinity, and if c is equal to 0, then that's just the nth derivative of 0 divided by n factorial. And instead of x minus c to the power of n, it would just be x minus 0, or just x to the power of n. Okay, so if we expand that a little bit, when n is equal to 0, that's just our function because it's say the 0th derivative. That's just f of 0 divided by 0 factorial times x to the power of 0. That's just f of 0. N is equal to 1, so that's plus the first derivative at 0 divided by 1 factorial times x to the first power, which is just x. When n is equal to 2, that's the second derivative at 0 divided by 2 factorial times x squared. When x is equal to 3, that's the third derivative at 0 divided by 3 factorial times x to the third power, and it just keeps on going. So just making that one little change of making c equals 0 turns this from the Taylor series to the Maclaurin series. Excuse me. Excuse me. All right. So let's say, for example, we wanted to find the Taylor series expansion for the function f of x is equal to e to the power of x at x is equal to 4. So we know that our Taylor series is f of x is equal to f of c plus f prime of c divided by 1 factorial. And actually, you just leave it as f prime of c, but I just do that to keep up the count, times x minus c plus the second derivative at c divided by 2 factorial times x minus c squared plus the third derivative at c divided by 3 factorial divided by x minus c to the third power. And of course, it keeps on going, but we're just worried about the first 4. Okay, so at x is equal to 4, remember this is just your x is equal to c. So c is equal to 4. So that means your f of x is just equal to f of 4 plus f prime of 4 divided by 1 factorial. And make that factorial a little bit more factorial-like. There we go. Times x minus 4 plus the second derivative at 4 divided by 2 factorial times x minus 4 squared plus the third derivative at 4 divided by 3 factorial times x minus 4 to the third power. And it keeps on going, but we're only worried about those 4. Okay, now this one's probably one of the easier ones because the derivative of e to the power of x is e to the power of x. The second derivative is e to the power of x. Third derivative is e to the power of x. So that one's pretty easy by comparison. So we know our f of x is equal to f of 4 is e to the power of 4. Plus the first derivative at x is equal to 4 is also e to the power of 4. You can say divided by 1 factorial, but instead of doing that, we'll just make it e to the power of 4 times x minus 4. Okay, we know the second derivative is e to the power of x, so the second derivative at 4 is still e to the power of 4, divided by 2 factorial, which is just 2. So we could say times 1/2, we can just make it divided by 2, completely up to you. Times x minus 4 squared, plus, again, we know the third derivative is e to the power of x, so that's e to the 4th power divided by 3 factorial. So e to the 4th power divided by 3 factorial is 3 times 2 times 1, which is 6. Times x minus 4 to the 3rd power. And it keeps on going, but we're only worried about the first 4. And they usually tell you if they want the first 4, 5, 3 terms. And this is your Taylor series expansion. For f of x equals e to the power of x at x is equal to 4. Okay, any questions on that one? All right, we should be able to get one more example. Anyone still writing? All right. So let's say, for example, if we wanted to find the Taylor polynomial, p sub 2 of x for f of x is equal to 3 times cosine of 2x at x is equal to pi over 3. Now, a quick note about the notation. You see p sub 2 of x. That just means you're going up to the second derivative, that term. So that's just f of c plus f prime of c over 1, we'll just call that f prime of c, times x minus c, plus the second derivative at c divided by 2 factorial times x minus c squared. So if it had p sub 3 of x, we'd go one more to the third derivative term. Okay, so we know that f of x is 3 times cosine of 2x. And f prime of x is the derivative of cosine, which is negative sine, times the derivative of what's inside, which is 2. So that gives us negative 6 times sine of 2x. And our second derivative, the derivative of sine is cosine, so that's negative 6 times cosine of 2x times the derivative of 2x, which is 2. So that gives us negative 12 cosine of 2x. Okay. Now at pi over 3, so at x equals pi over 3, we know that f of pi over 3 is just 3 times cosine of 2 times pi over 3, which is negative 3 over 2. Our derivative at pi over 3, so f prime of pi over 3 is negative 6 times sine of 2 times pi over 3. Which is negative 3 square root of 3. And for our, got to put my second derivative there. Now our second derivative at pi over 3, that's negative 12 times cosine of 2 times pi over 3, which is equal to 6. Okay, so for this one, our p sub 2 of x is equal to f of pi over 3 plus f prime of pi over 3 times x minus pi over 3 plus the second derivative at pi over 3 divided by 6 or you could just say 2 factorial times x minus pi over 3 squared. Okay, so we can simplify this. So our p sub 2 of x is equal to f of pi over 3, which is negative 3 over 2, plus f prime of pi over 3, which is negative 3 square root of 3, times x minus pi over 3. And let me clean that up a little bit. X minus pi over 3 plus the third derivative at pi over 3. Did I write 3? I meant to write 2. This should be the second derivative at pi over 3, which is equal to 6 divided by 2 factorial, which is just 2 times 1, which is 2, times x minus pi over 3 squared. So if we simplify it, we have p sub 2 of x is equal to negative 3 divided by 2. And we can just change that to minus. Minus 3 square root of 3 times x minus pi over 3 plus 3 times x minus pi over 3 squared. All right, any questions on that one? All right, so we will go ahead and stop there, and we will pick back up on Taylor and Maclaurin series tomorrow. All right, you have a good night.
Thank you.
Oh, sure. Yeah, I'll pull it down. Is that good? Oh, all right, you're welcome.
That's a question.
Sure.
How is the final going to be structured for this class? Do you have that?
Yep, we're gonna meet in the computer lab, and pretty much just like the homework, you'll have the final questions look just like it'll literally be from Newton.
Oh, like from Newton?
Yep, it'll be
Okay,
from Newton.
and then we can bring our calculator, you said?
Yep, you can use your calculator, and you can bring one sheet and fill it up with whatever you like.
Like one standard paper?
One standard 8.5 by 11 sheet. I'll send out an announcement kind of telling you everything.
All right, sounds good. Thank you.
You too. Yep, for the final, you will be allowed one 8.5 by 11 sheet of paper to write down whatever you like to use on it. Yep, and you can bring your calculator. And as long as it's a calculator without a computer algebra system, you're okay. So you wouldn't be able to use a TI-89 or the Inspire CAS. But any other calculator, as long as it doesn't have a computer algebra system, you're okay. I know my TI 83 Plus is old as dirt, so it definitely would qualify. You're welcome, Donovan.